Hi, 7.6, day 2. We're still talking about improper integral, but this time we're calling it something called type 2. Type 2 is when you have an infinite discontinuity, but it is not obviously an infinity. So, for example, we're going to be looking at times when the integral is discontinuous at the right end. So let's say b, there's a discontinuity there. What we'll do is we'll replace b with t, and we'll have t approach that b value from the left. You know, as we go down from a to b, we would be approaching from the left. So we'll take a one-sided limit. And then if a were to be a location of discontinuity, then we would approach a from the right. So look up again at my little number line. I approach a from the right when I'm on the interval from a to b. So we'll take a one-sided limit. Of course, if we do get a finite number for the integral is considered convergent. If we get infinity, then it is considered divergent. You could also have a discontinuity in between a and b. So you're on the interval from a to b, and there's some location c between a and b where a discontinuity is occurring. What you're going to need to do is split it up into an integral from a to c and then an integral from c to b. And what we'll do is we will take a one-sided limit as t goes to c from the left on the first integral, and then we'll take the limit as t approaches c from the right on the second integral. Here is an example. And this example, there is no evidence of infinity here. There's no infinity actually written. But what you need to do is examine the denominator. In the denominator, if x were to equal -2, we would have a vertical asymptote there. We would have a discontinuity because we cannot divide by 0. And that happens to be the lower limit of our integral. So what we're going to do is set up a one-sided limit. So let's use t because we were using it before, and we'll have t approach -2, and it will come in from the right. So put a plus symbol there, meaning we're coming in from the right, and take the integral from t to 14. I'm going to need a u substitution to do this one, so I'm going to let u equal x plus 2. That means du equals dx. Write that limit every single line. Don't leave the limit out. The integrand will become u to the -1/4. I'm going to leave the limits of integration off until I get back to the x world. The antiderivative of u to the -1/4 is going to be u to the 3/4 divided by 3/4, which is the same as times 4/3. I'm going to bring x back in. And therefore, I'm going to write my limits down again. Let's evaluate the limits. Substituting in 14, I'll get 4/3 times 16 to the 3/4. And then substituting in t, I'll get 4/3 of t plus 2 to the 3/4. For the first term, 16 to the 3/4. Of course, you could use your calculator if you're allowed to have it, but that is a fractional exponent. So the 3 is a power and the 4 is a root. The 4th root of 16 is 2, and 2 to the 3rd is 8. So this is really 4/3 times 8, which is 32/3. Now I will evaluate the limit. First I will have 32/3 minus. Now I'm going to substitute -2, and when I do, I get 0. So the answer is 32/3, and that means our integral is convergent. I have a warning for you here. You will have to check every integral from now on to determine if it is improper. So as I look at the next example, you should know right away that when x equals 0, this is undefined. 1 over x to the fourth is undefined. And 0 happens to be on the interval from -2 to 3. You have to pay attention from now on for every integral. If you did not catch that on this one, this is what will happen. Here I am doing it wrong because I didn't notice that 0 would be bad, okay? The antiderivative of 1 over x to the fourth, which is the same as x to the -4th, would be -1/3 x to the -3rd. Evaluate from -2 to 3. Okay, I'm going along not knowing that I have just included dividing by 0. I'll have -1/3, and then I'm going to substitute in the 3, so that's really 1 over x to the third. So 1/27 minus, now I'm going to substitute in -2, which will be -1/8, so that's -1/81st minus, and a common denominator would get me -35/648. So it looks like there's an answer. It looks like there's a value. It looks like this integral is convergent. But what should actually be happening is the right way to do this is to recognize that there's a problem at x equals 0. So you're going to split this up into two integrals and take the limit of each. So I'll choose to use the variable a. I'm going to have a approach 0 from the left, and I will start my integral at -2 and have it go up to a, where a is 0, but we're going to have a approach 0 from the left. Add the limit as b approaches 0 now, but we're going to come in from the right. So the integral will start with b and go up to 3. So if I just look at the first limit, the limit as a approaches 0 from the left, the antiderivative here is -1/3 x to the -3rd. Evaluate from -2 to a. Okay, I can just look at the first one first. I'll get the limit as a approaches 0 from the left of -1 over 3a cubed. So that is substituting a in. Now I'm going to substitute in -2, which is going to get me -1/8, which will be 1/24 after I multiply by 1/3. And you know, if I evaluate the limit now, the limit where a approaches 0, remember this fraction is like going to infinity now. So it's like I have an infinity plus the other integral, which I don't need to work out, because if one of them is going to infinity, then the whole thing is going to infinity. Really, this is divergent, and if you hadn't noticed that, you would have worked it out the wrong way and gotten an answer. For our next example, you should be aware that natural log x is undefined at 0. So immediately I'm going to set up a limit as t approaches 0, and look at your number line, 0 to 1. So we're going to head to 0 from the right. So that's why I'm going to put a plus sign there for my one-sided limit. And now it'll be written as the integral from t to 1. I don't know if you remember this antiderivative. If you don't remember it, we learned it in integration by parts. I'll let u equal natural log x, and I'll let dv equal dx. So the derivative of u is 1 over x dx, and v is x. We get the limit as t approaches 0 from the right of u times v would be x natural log x minus the integral of v du. When you multiply v times du, the x's cancel and you're left with dx. I'm not done taking the antiderivative, so I'm not going to put the limits on this yet. The antiderivative then is just x, and the limits go from t to 1. You have to write this limit out in front on every step. Substituting in 1 first, I'll get the natural log of 1 minus 1, that's like my first parentheses, minus, now I'll put t in for every x. I'll get t, natural log of t, minus t. If you realize that the natural log of 1 was 0, you could have written 0 there. I'm going to distribute that negative, so there will be a plus t on the end. I'm going to do a maneuver here. I'm going to move that plus t over by the -1. And maybe you notice by now if I tried to evaluate my limit, I'd have a problem with that last term because I would have a 0 times an infinity. You'd remember that is one of our indeterminate forms. So I need to do some algebra to deal with it. I'll keep writing my limit. I'm going to separate the expressions a little bit. Here is my limit as t approaches 0 from the right of the first two, so -1 plus t, like that could get evaluated, and then minus the limit as t approaches 0 from the right, and I'm going to change that expression. It was t times natural log t. I'm going to leave natural log t alone, but the t that was in front of it, I'm going to flip it over and put it in the basement. Now if you tried to evaluate that limit, you would get an infinity over infinity. So now that allows me to use L'Hopital's rule. I can go ahead with the other limit here in the front. The other limit in the front is just -1 plus 0. Okay, I'm doing L'Hopital on the back term now. So the derivative of natural log t is 1 over t, so that's the numerator. And the derivative of 1 over t is -1 over t squared. Flip the lower fraction up now, you would get 1 over t times -t squared over 1. So one of the t's is going to cancel. So I'm looking at the limit as t goes to 0 from the right of -t. And now taking the limit, I'm getting 0. So I'm getting -1 minus 0. Therefore, the answer is -1. The comparison theorem. What I want you to do is think about two functions f and g. And we're going to set it up so that f is greater than or equal to g. So in terms of a picture, I want you to think about f is greater than g. So graphically, f would be above g, like this. That would be an example of f being greater or equal to g. The theorem says if the integral from a to infinity is convergent on f. So look at f, and I'll set up an a, and what they're saying is if you take the area under the curve f from a to infinity and you get a value, it's convergent, then that makes sense that g would be convergent also, because the area under g would even be less than the area under f. One example we have of a convergent function was the first one we got when we started talking about this. Do you remember the curve y equals 1 over x squared? When we looked at that from 1 to infinity, we found that this was convergent. Well, if you had another curve that was underneath that one, so the area under that curve would be even less, and that would make it convergent. If you know your function, in this case f, is convergent, then g would be convergent as well, as long as the condition is met that g is smaller than f. So we will have to show that. Conversely, if g were to be divergent, okay, g is lower down, it's closer to the x-axis. If g is divergent, then of course anything above g would be divergent as well. I will use our other example from earlier on in our notes. Do you remember the function 1 over x? 1 over x, when we started at 1 and we took the area going to infinity, we found this to be divergent. The curve was not coming down and hugging up against the x-axis fast enough. So you can imagine, if we had a curve above that, well, that one's not going to get any closer to the x-axis if it's up above it or equal to it. So another function that's greater than a divergent function is going to be divergent as well. Number 58 is my example. The first thing I'm noticing is that I have an infinity here. If I can come up with an appropriate integral to compare with, something I'm familiar with, then I can get out of working out the integral. I'll write that down. That math problem looks like x over x cubed, doesn't it? It looks a lot like x over x cubed. And x over x cubed is the same as 1 over x squared. And guess what? We know something about 1 over x squared. We know that it converges on the interval from 0 to infinity. And it's because of that exponent. Do you remember that property where we had 1 over x to a power? And if the power was greater than 1, then the function would converge. If the power was less than 1 or equal to 1, then it would diverge. Once you have a familiar integral to compare with, set up your comparison. Take your math problem, x over x cubed plus 1, and compare it to this one. So this is 1 over x squared, also known as x over x cubed. I'm noticing that the denominator of the first fraction is greater than the denominator of the second fraction. Now the numerators are the same, so the only thing to really look at is the denominator. If the denominator in the first fraction is greater, that means the fraction is smaller. So this is a less than. I'm showing that our function is less than our comparison function. Okay, look back at our theorem again. If I can show that g is less than f and I know f converges, so I need to show f converges, which I already did. I already mentioned how f converges. Then I can say that g also converges. You need to have this line with a comparison with an inequality and state that the integral from 1 to infinity of our comparison integral converges. I already wrote y up here, so if you didn't write y already, you'd have to write it somewhere, and you could do it now if you didn't do it up there. Therefore, our integral from 0 to infinity converges by the comparison test. In your work, you will have to mention the comparison test. Key to this one was, when I looked at our math problem, I saw that I had an x over x cubed here, and when you reduce that, you get 1 over x squared, and 1 over x squared is one of those to help me make comparison. Just like 1 over x will be a good one for you to make a comparison.